Good afternoon, class. We are looking at exam 4 review, chapter 4, application of differentiation, chapter 5, integrals. We're also going to cover 6.1 area between curves. So exam 4, covering chapter 4.7 to 4.9, 5.1 to 5.5, and 6.1. Here's the first part, 4.7 through 4.8. 4.7, optimization problems. 4.8, Newton's method. So these are the sections we are covering, as it was mentioned, from 4.7 to 4.9, 5.1 to 5.5, and 6.1. So for now, the first part, 4.7 and 4.8. As you can see, there are many differentiation formulas that by now, I believe you are very comfortable with that. Here's the linearization. Here's the delta y versus dy. And delta y is change in y along the curve. Dy is the change in y along the tangent line. Dy is by definition f prime of x dx. Delta y is f of x plus delta x minus f of x. And we approximate delta y by dy. Linearization refers to finding a tangent line, and you have to find the tangent line. You can go with the point slope. Those are also the definition for E. The concept of optimization is about maximizing and minimizing things. For example, you want to maximize profit, you want to minimize cost. So, for example, find two numbers whose sum is 54 and whose product is a maximum. You look for the objective function, maximize P, which is x times y. We are assuming the numbers are x and y. And the constraint is that they must add up to 54. X plus y is 54. If 5400 pi inch squared of metal is used to construct a cylindrical storage drum, what is the maximum possible volume? Well, in this case, you're dealing with a cylindrical shape, radius r. This is the height. Volume is pi r squared h. And we want this to be maximize the volume. Subject is that we have this much, 2 pi r squared plus 2 pi r h equals 5400 pi. This is the surface area. I want to make sure we understand how we arrive at it. If you open this up, it becomes a rectangular shape where the width is, or you can say the length is 2 pi r, then times the h. And then the area of the bottom is pi r squared, so is the top 2 pi r squared. That's how we arrive at this. Here's another example. A farmer wants to fence a rectangular field beside a river with 2,400 feet of fencing. The river itself will be one of the four sides. What dimensions will give the largest? I'm going to go over this one with details, but there were some examples that you saw. So what I want to mention, you have to do the setting, you have to do the drawing. So for example, here, you say this is x, this side is y, we don't need anything here. Here's the area that you want to maximize. So you want to maximize the area equals x times y. Given that 2x plus 1y, not 2y, because this side doesn't need it, equals 24. So we solve for y. We put it into this function. This function is a function of two variables, x and y. Now it becomes a function of one variable. And the reason x is between 0 and 1200, number one, x represents dimension must be positive. Number two, if you set this parenthesis equal to 0, gives you 1200. When x is 1200, this becomes 0, so it can't be 1200. And if it's larger than that, it becomes negative. So you have an open interval of 0 to 1200. You distribute the x because you want to differentiate, and it's easier to do so. So we get 2400 minus 4x as a prime. When you set it equal to 0, the critical point is 600. We have an open interval of 0 to 1200 and only one critical point. So when you do the first or second derivative test, not only what you receive is a local, also it's an absolute. Now, is it max or mean? You have to do the test. It's easier to do the second derivative test. A prime is this, a double prime is -4. Negative means concave down, means maximum occurs at that point. So maximum occurs when x is 600. So if you plug it into this or this one, gives you y, which is 1200 feet. So the dimensions are 600 by 1200. And therefore, the maximum area is equal to the product of the two. That's how you handle a case like this. We are going to move on and look at more examples of optimizations. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions that minimizes the amount of material used. The objective is to minimize the surface area, the concept of gift wrapping. First and foremost, I want to remind you this is a rectangular solid. The volume is the width times the length times the height. The surface area, we have 6 sides. Width times the length plus height times the length plus height times the width, and then times 2 because we have 2 sides of each. And if all sides are identical, we call it a cube. The volume is s cubed, surface area is 6s squared. For this one, the surface area would be x times h, and there are 4 of them. The walls are identical because the base is a square. Then plus, the bottom is x squared, so is the top. So it would be 4x squared, 4xh plus 2x squared. But since it says open top, then we don't need the top plus 1x squared. So simply x squared. The objective is to minimize s, which is 4xh plus x squared. And the constraint is that we have the volume x squared h, x times x times h, the volume of 32,000. This is the translation of the question. So to solve this, we solve for h first, and we put it into s in order to make it a function of one variable. This x cancels out, and this becomes x. 4 times 32,000 is 128,000 over x. Because we want to differentiate, we are going to take the x up, make it x to the power of -1. And here's the domain, because x represents dimension. Dimensions must be positive. X, Y, Z, whatever. Differentiation. S prime would be the product of these two, -128,000 x to the power -2 plus 2x. Because we want to find the critical points, we're going to take this down. Common denominator is x squared. So minus 128,000, 2x times x squared is 2x cubed. And a fraction is 0 when the top is 0. A fraction is undefined when the bottom is 0. The bottom 0 gives you x equals 0, which is not in the domain. The top is 0, which means two x cubed is 128,000. X cubed is 64,000. X is the cube root of that number, which is 40 centimeters. And you always write units if units are given. Now, to prove this is a max or mean, you have to go with the first or second derivative test. Remember, first derivative test requires a sine graph. So let's go with the second derivative test. Here's S prime. S double prime would be the product of these two, which is positive 256,000 x to the power minus 3 plus 2. Now we have to plug in 40 and it becomes positive. Here's the reason. This one class is 256,000 over x cubed plus 2. So when you plug in 40 here, you don't even have to know the answer. This becomes positive plus 2 is positive because we just want the sign. Although it's easy to see that's 4 and 2 becomes, this becomes 6. Concave up, because it's positive, that means minimum. Okay, so it looks like that, concave up. So that's the minimum. The minimum occurs when x is 40. What is h? Either use this formula or this formula, and h becomes 20. So those are the dimensions. What would be the minimum surface area? You can put it into this formula. Okay, so x is 40, h is 20. Put it into the formula to find the surface area, which is 4,800. 4 times 40 times 20 plus x squared. What is the minimum distance between the two parabolas? Y equals x squared plus 1, y equals x minus x squared. You have to have a rough sketch of both. So y equals x squared plus 1 is y equals x squared shoot up by 1. So this one is, for example, the location 0, 1. And this one, it opens down. You can calculate x equals minus b over 2a as the location of a vertex and looking like that. So we want to find the minimum distance between the two. Somewhere there. We don't know where they are. But that is a vertical distance. The first one has coordinates x and x squared plus 1. The second one has coordinates x and x minus x squared. And basically, when it's a vertical distance, just the difference between the y coordinates. This is the vertical distance. X squared plus 1 minus x minus x squared. If you have any doubts, of course, you can again use the distance formula. Okay. So let's rewrite this as minus x plus x squared as 2x squared minus x plus 1. And x can be any number. We show it appears it's on the right side and therefore x is positive. But what if we are wrong, it's on the left side? So let x be any number, can be any number from negative to positive infinity, which makes it an open interval. V prime is 4x minus 1, and we set it equal to 0. So x becomes 1/4. So at x equals 1/4, we have one critical point and one critical point only. Is this going to maximize or minimize? We don't know. We must do the first or the second derivative test. Second is the easiest because v double prime is 4. So it is important to understand we have to really plug in, but there's nothing to plug in, so it's 4. Positive means concave up. Concave up, looking like that, means minimum. Concave. Remember, concave up, looking like that. So the minimum occurs when x is 1/4. Now, what is that minimum distance? Put it into this. So let's plug in 1/4 here. Minimum at x equals 1/4. So 1/4. So the absolute minimum would be the v at 1/4. 1/4 squared plus 1 minus 1/4 minus 1/4 squared. Or just put it into this formula. Either this one or the simplified version makes no difference, class. So maybe easier that I go with minus 1/4 and plus 1/16. And 1/16 and 1/16 is 1/8. 1 minus 1/4 plus 1/8 gives us 7. So that's easy to do, and it's elementary algebra, so just you can do it yourself. A cylinder is inscribed in a cone with height h and base radius r. Find the largest possible volume of such a cylinder. So here's the cone, conic shape. Here's the cylinder inside that. The cone has the height h, the radius r. So if we call this x and call this y, this distance is h, and this is capital R. We're just making things up. We want to find the largest possible volume of a cylindrical shape, which is pi r squared h. So pi, capital R squared, capital H. That's what we want to maximize. So largest possible volume. So R is the same as X, right? Capital R is the same as X. What about capital H? Is the same as lowercase h minus y. I hope everybody can see that. Therefore, we are going to replace the capital R with X, capital H with H minus Y, and that's what we are going to maximize. The volume is pi x squared times H minus Y. Look at this shape. This is the large triangle, and this is the small one inside. Clearly, the small one and the large one, okay, I made it larger so it's easier to see, are similar figures where this distance is y, this distance is x. For the big one, this distance is h. For the big one, this distance is r. So x over r is y over h. Again, this is one way to write it. Those are similar figures, similar triangles, because two sides are parallel, okay? And one side. In essence, two sides are parallel, these two and these two. So x over r is the same as y over h. Now, in this, we want to use one of those variables. V is a function of x and y, but if we solve for y, which is x times h divided by r, I'm assuming everybody knows this is a cross product. And we are going to replace this and make it a function of x. Let's distribute. So pi hx squared minus pi h over r x cubed, and x can be between 0 and r. Imagine, can x possibly be as much as r? No, it has to be less than r. There is no way. So x is between 0 and r, and that's extremely important to understand. So now we are going to differentiate. V prime of x is pi h times 2x, or 2 pi hx, minus pi h over r times 3x squared. And we can take the pi hx out, pi hx. This gives us 2. This gives us 3x over r. I hope you can see that. It's just factoring pi hx. So you're factoring pi h and one of these x's, okay? And one of them remains. When you want to find the critical points, you set this equal to 0, and we get two answers. One of them x is 0, one of them 2 equals 3x over r, or x is 2/3 r. So again, I want to quickly show you either this one is 0 or this one is 0. The parentheses, that means 2 equals 3x over r. So if I multiply by r, I get 2r equals 3x. And if I divide by 3, I get 2/3 r. Okay, everybody. So that's v prime. So there are two answers. We can't have zero. That means zero is out. We have only 2/3 R. So does that represent max or mean? We don't know. We're going to take the second derivative, v double prime. This is v double prime of x. Which is 2 pi h minus 6 pi over r. This one class. Let me just erase it and show you. First of all, this is v double prime. Secondly, this is 2 pi hx minus 3 pi h over r times x squared. So this gives you just 2 pi h. This gives you 3 pi h over r times 2x. That's how you arrive at this, okay? Now you are going to plug in 2/3 r. Again, this is out. You plug in 2/3 r. And it becomes negative. I will quickly, I can show you that. So this becomes, if I plug in 2/3 r, two pi h minus 6 pi h over r times 2/3 r, right? Which is 2 pi h minus r cancels out r. We have 12 pi h divided by 4, or 4 pi h, which makes it negative 2 pi h. As you know, pi is positive, so is h. So the negative makes it negative. So that's a proof. What does it mean when it's negative? It's concave down. When it's concave down, then maximum occurs at x equals 2/3 r. We want to find the largest possible volume. We have to plug into the volume. And to do so, I'm going to plug in here. Or here. So let's do it here because we have x here. So pi h x squared. I'm going to use this one, okay? And for this one, I'm going to factor out pi h x squared. I get 1 minus x over r. And I will replace the x with 2/3 r. So 2/3 r divided by r becomes 2/3. So 1 minus 2/3. Please understand, when we plug in 2/3 r instead of x, the r cancels out. And 1 minus 2/3 is 1/3. So we have pi h times 2/3 r squared times 1/3. 2/3 becomes 4 over 9 times 1/3 becomes 4 over 27. Pi h remains r squared. So 4 over 27 pi r squared h. I hope everybody's okay with this calculation class. It's pretty straightforward. Newton's method. Consider a function as it crosses the x-axis. So this function, here's one root, here's another one, is the x-intercept or the root of the function. Newton noticed that tangent line close to the root crosses the x-axis nearby. Tangent line intersection. We remember the formula, y minus y1 equals m times x minus x sub 1. So at this point, okay, notice that the tangent line crosses the x-axis at this point, which is not the root for the curve, but this is the root or the x-intercept for the red line, which is a tangent line. Using the point slope, y minus y1 or y minus f of x1 equals m or f prime of x1 times x minus x sub 1. So this formula, this is the point slope class. y1 is f of x1. M is f prime of x1. If you want the x-intercept, this is the line. We haven't simplified the line. We can by using this and taking it to the right. But let me explain what happens. If you want an x-intercept, you set y equal to 0. So this tangent line, you set the y equal to 0, gives you this location. So this is 0. If you divide by this, it gives you x minus x sub 1, gives you the parentheses. This is the same as this one. If you move the x sub 1 here, that gives you the x that you're looking for, which is the x-intercept. Use that point as a second and usually better estimate for the root of the function. So again, this is just some point which was created by the tangent line as it crossed the x-axis. This is the root, the x-intercept for the tangent line, not for the function. But it's an approximation for the real root we are looking for. Now, this one, if you do the next tangent line for the curve at this point. So at this point, okay, that's the idea. If you draw a tangent line, so it appears it's hard to do the drawing. Gives you a different point, which seems to be closer. This point, which seems to be closer. So now, same as this one. X sub 1 was this, right? Now x sub 2, you replace this. X sub 3, you replace x sub 1 with x sub 2. So this is f of x sub 2 over f prime of x sub 2. And repeated application of this process is called Newton's method. It results in the following: x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. In other words, if you want to find the next one, use the previous one minus, evaluate the function at the previous one over f prime at the previous one. That's the meaning of it, everybody. So that was the concept of this Newton's method. So again, just to repeat that, consider a function as it crosses the x-axis, the root. Newton notices the tangent line close to the root, crosses the x-axis nearby, tangent line intersection. F x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So that's what we have here, everybody. From here's some x, let's say x sub n. At that point, if you draw a tangent line, it creates a new point, and we can find a tangent line at that point. So notice here somewhere we start, we draw the tangent line. So if we call this x sub 0, then the next x-intercept of tangent line is this next point. At that point, we draw a new tangent line. X sub 2 is not the root. Remember, the root is the red point, but it's getting closer and closer. So we use the linearization or the tangent line using that formula. Then for the second point, so x sub 2 is x sub 1 minus f of x sub 1 over f prime of x sub 1. X sub 3 is x sub 2 minus f of x sub 2 over f prime of x sub 2. Okay, the next point. And this thing continues, and it gets better and better approximation. Now, the concept is very straightforward. When the numbers get involved, it becomes tedious to do it by hand. So here's the program I'm going to show you quickly. It's a calculator program. Y sub 1 equals f of x. So you put y sub 1 equal to f of x in a graphing calculator such as TI. Y sub 2 equals f prime. And then you store x sub 1, the first point in x. Then x minus y1 over y2, store it in x, and you enter repeated. This I will show you in a moment, but this is in case it's getting involved and you have to do a lot of repetitions. You can use that to speed up your process for your home. Calculate 3 iterations of Newton's method to approximate a 0 for this function f of x equals x squared minus 2. They are giving us x sub 1. They don't have to, but when they give us, it becomes easier to get that started. So let's do that. So f of x is x squared minus 2, and f prime is 2x. The concept is this. You have this function y equals x squared, bring it down by 2, becomes y equals x squared minus 2. It shows a part of that. And x sub 1 is this point, 1. And at that point, on the function or curve, we draw a tangent line. It gives us this point, and that's a new point, or x sub 2. This point is x sub 2. So I hope everybody can see how we arrived at x sub 2. Now we are going to calculate the value of x sub 2 using, in essence, the tangent line, okay? Which is the synopsis of the tangent line giving rise to Newton's method. So according to this, x sub 2 equals x sub 1 minus f of x sub 1 over f prime of x sub 1. So if x sub 1 is 1, replace it. So we want 1 minus f of 1 over f prime of 1. Again, I'm going over all the details so we don't miss anything. Now f of 1 If you plug in 1 here, you get 1 squared minus 2, which is -1. So this is -1. F prime of 1, 2 times 1, this is 2. As you see, this is plus 1 and 1/2 is 1.5. So x sub 1 is 1, x sub 2 is 1.5. 3, so we have 2 more to go. X sub 3 is x sub 2 minus f of x sub 2 over f prime of x sub 2. So this is 1.5. At that point, okay, if we draw a tangent line, it looks something like that. As you can see, it's hard to even pinpoint x sub 3. Class x sub 3 is somewhere here, almost the same as the x-intercept for the curve, almost. Let's plug in. So x sub 2 is 1.5. If I plug in 1.5 here and 1.5 here, let's see what happens. F of 1.5, 1.5 squared is 2.25 minus 2, it becomes 0.25. If I plug it here, 2 times 1.5 is 3. So 1.5 minus 0.25 over 3. Okay, this one plug it into this one plug it into this. Use a calculator to find this and subtract it from 1.5, and we use a bunch of decimals. Normally they tell us how many. So now it's 1.416667. So it's this number, which is very difficult, this point to show, which is closer. We do one more because they want 3 iterations. We did one of them, we did one more, and now it's the last one. So using this formula, obviously. So put this number here minus f of this number over f prime of this number. Clearly, you have to put this number here, squared minus 2, use a calculator. You have to multiply this 1 by 4, 2. It's almost 2.8. And then you do the math. As you can see, it's extremely close to that 1.414216. And this is the last one we do for this question. So I hope everybody's clear how we arrived at the answer. We can use the Newton's method to approximate, let's say, the 8th root of 500. Again, it's sort of finding the tangent line. I want you to know that. So first, to approximate this, we set this equal to x. Let x represent that. If I raise it to the power of 8, both sides, I get x to the power of 8 equals 500. If I bring it to the same side, x to the power of 8 minus 500 is 0. Let f of x represent that. Now, if I find the x-intercept for this, or the root for this function, is the same as solving this. First, we need to understand this. Okay? To solve this is the same as finding the x-intercept for this. To do so, we need f prime of x, 8x to the power of 7. And then the formula is x sub n plus 1 is x sub n minus f of x sub n, which is x to the power of 8 minus 500 over f prime, which is 8x to the power of 7. So I'm going to write this for some numbers such as n, x sub n. Some numbers such as x sub n. Now this is general. So if I want x sub 2, If I want x sub 2, this becomes 1, this becomes 1, this becomes 1. And so where should I begin? Somewhere. 2 to the power of 8 is 256, 3 to the power of 8 is 6,561. So you start with one of those. If, for example, we let that be 2. We start with number 2. Again, we had to choose on our own. Because of the program I gave you, really, even if you pick a number which is off, you can do it fairly easily, but has to be somewhat close. So x sub 2 is x sub 1 minus x sub 1 to the power of 8 minus 500 over 8x sub 1 to the power of 7. Let's replace x sub 1 on the right side, all of them with number 2. We know this is 256, subtract 500 from it, and becomes negative 244, 2 to the power of 7. This is 2 cubed, this 2 to the power of 10, which is 1024. And negative makes it positive. So that results with a bunch of decimals. Because they want 8 decimals, I'm going to use many, okay? So you really have to do more. Now, if I want to get the next one, I would say x sub 3 is x sub 2 minus x sub 2 to the power of 8 minus 500 over 8, x sub 2 to the power of 7. Now, what is x sub 2? This is the number. And that's what I mean. It's very difficult now. If I want to use that number, it's going to take a long time. It's not, it's going to be a long process. It's tedious. It's not that it's difficult. So that's why we're going to use the program that I told you. So we're going to let y1 represent f of x. So y1 would be x to the power of 8 minus 500. Y2 will be 8x to the power of 7. So you put x sub 1. We decided to go with 2, store it in x. Okay, so we store 2 in x. Now we put x minus y1 over y2. It's this side in essence. Back into x, and we repeatedly press enter. And when we do that, this is what we get. And since we want to 8 decimals, we are going to continue until they agree to 8 decimals. Notice 1, 2, 3, 4, 5, 6, 7, 8. They agree to 8 decimals. And both of them next to it is 6. So it goes up. If I want to answer that, this 7 must change to 8. So this 7 has changed to 8 because next to it is the last one is number 6. So the 8th root of square root of 500 is 2.1745592. Very straightforward. Here's the last question. Use Newton's method to approximate the positive root of this function 3 sine x equals x to 6 decimals. You have to sort of graph to have an idea what you're looking for. And the graph is really not that difficult. If you draw 3 sine x, which means sine x, and then take it up by 3, right? Multiplied by 3. That's why you can figure out what this one is. This is pi over 2 and 1 times 3, because it's so pi over 3 and 3, okay? So, and y equals x goes through the origin. So there are 3 points of intersection. And so this is 0, 0. And by the way, you know sine of 0 is 0, and 3 times that is 0. So that works. So this is 0, 0. You want to find these 2, but we just want one of them because it's asking for the positive root. So we want to find this root. Okay. So what we are going to do, we are going to bring everything into the same side, left or right, doesn't matter. 3 sine x minus x represents the function f of x. We differentiate it because we're going to need it for the Newton's method. F prime is 3 cosine x minus 1. And so in this formula, we are going to put x sub n plus 1 is x sub n minus 3 sine of x sub n minus x sub n over 3 cosine of x sub n minus 1. It's a general form. And we want to use some initial value. This is clearly close to 2, but it's not 2. So let x sub 1 be 2. So x sub 2 is x sub 1 minus 3 sine x sub 1 minus x sub 1 over 3x cosine of x sub 1 minus 1. And we use number 2 because it's the x coordinate for this and the point of intersection is very close. Obviously, you need to use a calculator for that. So if x sub 1 is 2, x sub 2 ends up being this number. And I'm putting just a few decimals, but ultimately, you really have to put more and then make a decision, okay? Now, for x sub 3, if I want x sub 3, it's x sub 2 minus 3x sub 2 minus x sub 2 over 3 cosine of x sub 2 minus 1. But at this point, I'm going to use the methodology that I told you. So y1 is 3 sine x minus x. So I'm going to put the function into y1. Its derivative into y sub 2. So y sub 2 represents f prime of x. And now this formula, x sub 1 goes to x. X sub 1, the choice was 2. We're going to store the 2 in x. And then x minus y1 over y2, store it in x, gives you this number. And if you click on it again, that gives you x sub 3, everybody, because we have x sub 1 and x sub 2. X sub 3 is this number now, according to this. And I just what I did, after 9, I changed the 4 to 5 because this is 8. Do it one more time, couple more times. And we wanted up to 6 decimals. So 1, 2, so here's the 6 decimals, okay. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. As you can see, they are identical. Because the first 6 decimals are identical, we stop. Next to this is 8 and it goes up to 3. The same thing here, 6 goes up to 3. And that is the approximation of x sub 4, which is the x sub 5 as well, with only 6 decimals.